this workshop is kind of the idea of this workshop to gather friends of our lab who regularly visited our lab or who even worked at our lab. And the first speaker is a good friend of our lab and who even worked a lot with us, István Tomon, and he will speak about Ramsey properties of algebraic graphs and hypergraphs. So, István, please.
Okay. So thanks, Sasha, for organizing this session. So yes, I will talk about certain Ramsey type properties of graphs and hypergraphs that can be defined in an algebraic way, and everything I talk about is joint work with Benny Sudakov. So as you probably know, whenever we talk about Ramsey theory and Ramsey type properties, we talk about the question that given a graph on n vertices, how large of a clique or an independent set can we find in this graph? So the classical result of Erdős and Szekeres tells us that every graph on n vertices contained either a logarithmic size clique or a logarithmic size independent set. And later, Erdős showed that this bound is essentially the best possible. So his celebrated probabilistic argument says that if we consider the random graph Gn1/2, so we look at the graph on n vertices in which we include every edge independently with probability half, then this graph contains no clique or independent set of size larger than 2 log to n with high probability. So we have these two nice results which basically settle this problem for general graphs, but this is still a bit annoying that for this upper bound we only have this probabilistic construction. So one would imagine that for such a basic problem it shouldn't be too hard to come up with some explicit or deterministic construction. So unfortunately, this problem turned out to be extremely difficult. So despite the fact that it's extensively studied, still to this day we don't have deterministic constructions of graphs which achieve this logarithmic bound. So this question is still open, and the currently best known bounds are due to recent results of Chattopadhyay and Zuckerman and independently Cohen. Okay, but let's say that you want to construct such graphs which have good Ramsey properties, maybe not logarithmic, but with some reasonably good Ramsey properties. Then what kind of techniques or what kind of ideas can you use to construct these graphs? So one natural approach to construct such graphs is to use algebraic tools. So the first construction of explicit Ramsey graphs, which would be this polynomial bound, namely that it has smaller cliques and independent sets than n to the alpha for every positive alpha, is a construction of Frenkel and Wilson. So they consider set systems and intersection patterns of set systems, but their construction is very much algebraic in certain sense. So in particular, I will talk about this construction in a few minutes. So another very good candidate for Ramsey graphs are polygraphs. So if you don't know, polygraphs are the graphs whose vertices are just the residues modulo some prime of the form 4k plus 1. And then we connect two of them by an edge if their sum is a quadratic residue. So it is conjectured that such graphs have logarithmic size cliques and independent sets, but we were unable to prove that. So also, this is a bit of a side note, but we have these recent very interesting constructions of Colon, Farber, and Wittgerson, who consider the multicolor Ramsey number, and they provide some constructions which are not completely algebraic. They are like half algebraic, but half probabilistic. Okay, but so I was talking about graphs which are defined algebraically, but I have so far not really said what I mean by this. So what do I mean when I say that a graph is algebraic? So let me provide the following definition. So I will say that a graph is algebraic of complexity n d m, where n d m are positive integers, if the vertex set of G is a subset of some n-dimensional space over some field F, and the edges of G are determined by the zero patterns of M polynomials F1 up to Fm, each of degree at most D. So if you have not worked with this kind of problems, then this definition might be a bit heavy at first glance. So let me just give some details. What do I mean by this? So first of all, what do I mean by a zero pattern of a sequence of polynomials? So let's say we are given a sequence of polynomials, then what I can do is let's just take some x in the domain of these polynomials and let's just evaluate them. So let's write down f1x, f2x, dot, 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 fmx. So then I will get some sequence of elements of this field f. But in the sequence, I only care about which elements are zero and which are not. So if I see a zero, I keep it. If I see a non-zero, I put a star. So this will give a sequence of zeros and stars. And any sequence I can get in a way like this will be a zero sequence of these polynomials. Now this definition means that what we're going to do is, if we have two vertices x and y, which are now elements of Fn, then I will evaluate these polynomials at x and y. So I write down f1xy, f2xy, dot, 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 fmxy, which then gives a zero pattern. And if from this zero pattern alone, I can reconstruct whether this pair of vertices were joined by an edge or not. If I can reconstruct this from just the zero pattern, then I say that this graph is algebraic with these defining polynomials. So I hope this is clear, but in a second, I will also give you an example to get even more familiar with the definition. And so I will use one more notion. So I will say that a graph is strongly algebraic of complexity ND if this graph is just defined by a single polynomial of degree at most D. And I also want that I define it a way that I draw an edge if it does not vanish on this pair of vertices. So if this polynomial is non-zero, then I put an edge, otherwise I don't put an edge. So these are strongly algebraic graphs. And so let me show you an example of algebraic graphs, so namely, so first, so why I have these strongly algebraic graphs is that, so every algebraic graph of complexity MDM is just the Boolean combination of M strongly algebraic graphs of complexity ND. So many times when I will say some statement about algebraic graphs, I will just say something about strongly algebraic graphs and argue that, okay, I can get algebraic graphs by taking Boolean combinations. Okay, so now let me show you an example. So in particular, let me show you this construction of Frankel and Wilson. So they consider the following graph. So let's fix some p prime and consider the graph whose vertices are the p² minus 1 element subsets of an n-element ground set. And if we have two such sets A and B, then join them by an edge if the intersection is not -1 modulo p. So first of all, it can be easily seen that this graph is strongly algebraic of complexity n2 over the finite field fp. So as is true, so we can just identify these sets, which are the vertices of the graph, with their characteristic vectors. So with these 0, 1 vectors, where 1 denotes if we have an element and 0 if it's not an element. And then the edges are just defined by this single polynomial, which is the scalar product of the characteristic vectors plus 1. So we have an edge if this is non-zero and the non-edge otherwise. So but let me say that something which is less obvious, that this graph is also algebraic of complexity p² minus 1, 1, p² minus 1 squared over R, or actually over any large enough field. So in particular, this shows that the complexity of this graph does not depend on n, it only depends on p. So now it's a bit trickier, but it's still easy. So now what we do is, instead of looking at characteristic vectors, we will identify each set A with a vector of length p²-1 just by simply listing its elements. So if we have the set A, which contains the elements 1, 2, 4, then we just write down the vector 1, 2, 4. And then in order to define the edges of the graph, it is enough to just look at these simple linear functions fij xy equals xi minus yj. So what these functions do, they just compare the i's coordinate with of x with the j's coordinate of y. So if we write down these p²-1² linear functions, then the number of zeros will be the size of the intersection of the corresponding sets. So in order to reconstruct edges, we just need to count how many zeros we see, and if the number of zeros is not congruent to -1 then we put an edge, and otherwise we don't put an edge. Okay, so I hope this is clear. And so the reason why these Frankel-Wilson graphs are interesting is that they have pretty good Ramsey properties. So it follows from this Frankel-Wilson theorem of restricted intersections that these graphs do not contain any clique or independent set of size larger than this n to the 1/p+1. So in particular, by choosing p arbitrarily large, you can beat any polynomial.
István, can I ask a quick question again? Can you show again the definition of this algebraic, like in the order of this complexity things? I didn't memorize it. Okay, thank you. Just give me a second.
Oh, sorry. Can you repeat it?
Yeah, I just wanted to ask a second to look at it.
Okay.
Okay, so it's number of variables, degree, and the number of polynomials. This is the order.
Yes, so the degree m is the size of the field, and m is the number of polynomials. Yeah.
And can we go back to this d² minus 1, p² minus 1? Yeah, this one. Okay.
So these are just 1-degree polynomials. We live in a p²-1 dimensional space, and the number of functions is this.
Okay, now I see. Yeah, great, thanks.
And so the question we wanted to understand, or the problem we want to understand, is that so how good this algebraic construction can be as Ramsey graphs. So if we are given Ramsey graph with certain complexity, then what can we say about the size of the largest clique and independent sets? Almost the same question was already considered 20 years ago by Rónyai, Babai, Ganapati. So they proved that if we have an algebraic graph on n vertices of this complexity NDM, then either G or its complement contains a complete balanced bipartite graph of size some constant depending on the complexity times n to the 1/n+1. So this is not quite what we want, because instead of finding cliques or independent sets, they find these complete balanced bipartite graphs. But this theorem already says something very strong, because we also know that in the random graph Gn1/2, we can only find logarithmic sized complete balanced bipartite graph like this. So it already shows that these algebraic graphs are kind of far from these random looking graphs. And so what we wanted to understand is that how can we extend this result to really cliques and independent sets? And we managed to prove the following theorem. So we have an algebraic graph with usual complexity NDM, then can show that G contains either a clique or independent set of size some constant times n to the 1/α, where this alpha has the following dependence on the complexity. So it is the minimum of n times d times n and n squared m log d over log m. So here in the theorem of Ronyi, Baba, and Ganapati, they prove that this exponent only depends on n, and it depends in a very nice way, so it's only linear. So unfortunately, we weren't able to prove that, but at least we could show that it depends at most linearly on each of the parameters in the complexity. And also, the second part shows that it cannot depend too much on the degree of the graphs. So it can depend at most as a logarithmic function on the degree. So it shows roughly that if you want to cook up good Ramsey graphs, then it's maybe better to choose n to be large than to just increase the degree. And also this dependence of m, so unfortunately we couldn't get rid of it, and it's probably also, it shouldn't depend linearly on m either. But so this is what we could prove, and so I want to talk a bit later about the proof of this result and the ideas of the proof. But before that, I want to compare this result with some other results in a very close related family of graphs, which are called the semi-algebraic graphs. So semi-algebraic graphs might be a bit more familiar for many people in the audience, but so let me define this. So we say that a graph is semi-algebraic of complexity NDM if the vertices are elements of the n-dimensional real space, and the edges are defined by the sign patterns of n polynomials of degree at most d. So now the difference between algebraic and semi-algebraic, that we restrict our attention to the real space, but now we, instead of zero patterns, we actually look at sign patterns of polynomials. So when we evaluate the polynomials, we care about whether this number is negative, zero, or positive. And so the Ramsey properties of such graphs were also studied 50 years ago. So there was a very interesting result of Alompach, Nkasi, Radich, and Sharir proved that if we have a semi-algebraic graph of bounded complexity, then either G or its complement contains a complete balanced bipartite graph of linear size. So just to compare with the previous result, so this theorem only guarantees a polynomial-sized complete bipartite graph. But here, in the case of semi-algebraic graphs, you can actually find a linear size one. And also they argue that this property alone, so just containing linear-sized complete bipartite graphs, already implies that these graphs contain cliques or independent sets of polynomial size. So one might get this feeling that maybe semi-algebraic graphs are a bit more exotic than algebraic graphs, because instead of zero patterns, we have this freedom of looking at sign patterns. But interestingly, it turns out that in some sense, algebraic graphs can be more exotic. So for example, the first part of this theorem is just not true for algebraic graphs. So it's not true that in algebraic graphs you can always find linear sized complete bipartite graphs, and the construction is this well-known Erdős-Rényi orthogonal polarity graph. So I don't need this graph, which has complexity 3 to 1, and every biclique is of size m to the 3/4. So this graph is just the usual construction if you want to find a C4 free graph. So this is the C4 free graph with the maximum number of edges, and this also has this nice property.
István, do I understand correctly that the key point there is that the points are in Rn?
Sorry?
Do I understand correctly that the key problem or difference is that the points lie in Rn? Not in arbitrary fields.
Yes. Yeah, so this Erdős-Rényi graph, this is defined over a finite field of prime characteristics. Yeah. Okay, so this is about graphs, and before I talk about proofs, so the title of my talk was Ramsey properties of algebraic graphs and hypergraphs. So now let me also talk a bit about what happens for hypergraphs. So I only defined algebraic and semi-algebraic for graphs, but you can easily extend the definition for hypergraphs as well. And so already we don't have a good understanding of the hypergraphs Ramsey numbers of just general graphs. So there is the node result of Erdős-Radó and Erdős-Hanner and Radó, which shows that if this RRT denotes the smallest and such that any R uniform hypergraph on n vertices contains either a clique or independent set of size t, then we have these upper and lower bounds on RRT. So the upper bound is a tower of twos of size r with a linear function of t on top, and the lower bound is a tower of twos of size r-1 with a t-square on top. So there is an exponential gap between the lower and upper bound. But surprisingly, it was proved by Coleman, Fox, and Sudakov that actually for semi-algebraic graphs, we pretty much completely understand the growth of these Ramsey numbers. So they showed that if this RR and dm denotes the smallest and such that any R uniform hypergraph of complexity and dm contains either a clique or independent set of size t, then this function roughly grows as a tower of twos of size r-1 with some polynomial of t on top. So now it's natural to ask that what happens for algebraic hypergraphs. And somewhat surprisingly, it turns out that algebraic hypergraphs behave very differently. So actually these hypergraph Ramsey numbers of algebraic hypergraphs always grow at most polynomially, or always grow polynomially. And this actually follows from a result of Maldiaris and Shella, and also proved independently by Chernikov. So they proved that there exists some exponent alpha, which only depends on the complexity and the uniformity, such that any algebraic hypergraph of this bounded complexity contains a clique or independent set of size capital N to the 1 over alpha. So unfortunately, so both Maldiaris, Shella, and Chernikov, they come from logic, and they, in order to prove this, they use tools from logic, and the exponent they get is not quite explicit. So in this paper of Chernikov, it's completely inexplicit, and in this paper, it's something that actually we couldn't really read out. But turns out that one can choose this exponent to be a pretty reasonable function of the parameters. So with some simple combinatorial techniques, we could show that one can choose alpha to be roughly r squared times m plus d choose d. So unfortunately, we don't know how good this exponent is. So already it would be maybe nice to push this down to just constant NDM, which we had for graphs. But we also don't know how good this bound is. So it's not like we conjecture that this is the right bound, but already improving it, this would be interesting. Okay, so these are the two results I will talk about. So let me just give you a very rough outline of the proofs, if there are no questions. Okay. So one straightforward idea is to try to find some forbidden subgraph or subhypergraph in these algebraic graphs which have some simple structure. And it turns out that we could find the following graph as a forbidden in the subgraph. So now we are only going to consider strongly algebraic graphs. So these are the algebraic graphs that are defined by a single polynomial. And we can show that such graphs avoid the following graph as an induced subgraph, where S is at least M plus D choose D. So let me explain what this graph is. So first of all, we have a matching of size S, which are denoted, which formed by these edges. And then I have these dash edges, which only go kind of this forward way. So, and strongly algebraic graphs do not contain this configuration, but I want that these matchings are edges, but these forward-going edges are non-edges. And I actually don't care what happens with all the other edges. So these edges which I didn't mark, they can be either edges or non-edges, I don't care. So and the simple...
So it's like based on a half graph, right? And there is one edge also missing on the, one non-edge missing on the picture, right?
Yes, so the half graph, then you would want these edges to be edges.
Yeah. And the two last vertical edges should have also one non-edge between them, right?
Yeah, so this is some subgraph of the half graph. And it's this
of the matching, yes?
Sir?
S is the size of the matching.
Yeah, yes, thank you, yes. So S is the number of these edges. And roughly the reason is that we can avoid these graphs is that you can find the kind of matrix that corresponds to the edges of this algebraic graph, and in this matrix this would correspond to an upper triangular matrix. And so your argument is you just show that this matrix do not have large rank, but this upper triangular matrix would have rank at least S. So then this is the contradiction. So we get this forbidden subgraph. And it turns out that we can already say pretty strong things about just graphs that avoid this particular matching, and we don't assume anything else about them. So we can show that if we have a graph and vertices which avoids this matching MS, then G contains either a clique or an independent set of size at least onto the constant over S. And we can for hypergraphs, can find some appropriate analog of this MS, which is a bit more technical, but not that much more. And we can show that if we avoid those hypergraphs, then we get the same exponent. And so this actually alone already proves this result that we wanted, because our S was N plus D choose D. Yeah, sorry for jumping, and then we get this exponent, this N to the 1 over N plus D choose D roughly. But for algebraic graphs, this is not what we wanted, because we wanted something that is linear in the parameters. So we wanted 1 over NDM. And in order to do that, achieve that, we need to do something more, because it turns out that if you just look at these families of graphs which avoid MS, then this bound is the best possible up to the constant factor. So one can just consider usual probabilistic constructions that they will avoid MS, because MS contains a large empty bipartite graph. And so you cannot hope in general better than this. So, but then what can we do to improve this in the case of algebraic graphs? So one of the main tools we are going to use is going to be a lemma of Rónyai, Baba, and Ganapati about the number of zero patterns. So they prove that if we have a sequence of m polynomials from field Fn to F, and each of degree at most D, then the number of zero patterns of the sequence is at most md plus m choose n. So here, the way we are going to apply is this m is going to be different than rm, but the important thing about this function is that it grows as, if we fix n, then this number grows as a polynomial of degree at most n. And also let me mention, this lemma might be familiar to some of you, because this lemma is very reminiscent to the famous Milnor theorem on the number of side patterns of real polynomials. But while this is a pretty heavy theorem, so I think the proof of this requires some heavy algebraic geometry. The proof of this lemma is just half a page of clever linear algebra. So we are not using anything too deep at all. But why is this lemma useful for us? So this lemma roughly tells us that if we have a strong algebraic graph of complexity ND, then it behaves very similarly to a graph of VC dimension at most. So let me, again, sorry for all these definitions, but so now I have to talk a bit about what does it mean for a graph to be of bounded VC dimension. So first of all, so again, when we talk about VC dimension, again, we have to talk about set systems. So I hope a lot of you are familiar with all these notions, because otherwise I can imagine that it gets a bit heavy. But now let me talk about set systems. So we say that a set system shatters a set X if the projection of the set system into this set X gives the family of all subsets of X. And then the VC dimension of the set system is just the largest set which shatters. And then the VC dimension of a graph is the VC dimension of the set system generated by the neighborhoods of the vertices. Or sometimes they define this by the dual VC dimension, but I don't want to complicate things. So this is roughly what we want. And so this previous statement was that if we have an algebraic graph of complexity ND, then it is reminiscent of a graph which has VC dimension at most. And it turns out that for graphs of bounded VC dimension, there is a thing called ultra-strong regularity lemma. So this was proved in a number of forms, but in the strongest form, I think it's due to Fox, Spock, and Sook. So the usual regularity lemma for graphs says that we can partition our graph into a bounded number of parts, where this bounded number is some extremely huge, extremely fast-growing function of some parameter epsilon, such that between almost all parts we have an almost like random-looking graph. So now for graphs of bounded VC dimensions, we can do something much stronger. If we fix some parameter epsilon, we can partition our graph into a polynomial number of parts in 1 over epsilon. So into 1 over epsilon to the 2 parts, such that not only the graph between most pairs of parts is random, like it's actually either very close to having density 0 or very close to having density 1. So it has density on at most epsilon, or density at least 1 minus epsilon. And it turns out that the way our algebraic graphs can be compared to these graphs of bounded VC dimension is that one can prove basically the same regularity lemma for algebraic graphs as well. And so what our argument is that, so we will look at a family of graphs which satisfies this ultra-strong regularity lemma and also avoid MS. And we show that having this extra condition, this ultra-strong regularity lemma, boosts a lot how large of a clique or independent set we can find. So one of our main lemma is that if we have a graph on n vertices which avoids this matching MS and satisfies the ultra-strong regularity lemma with parameter n, which is, so n is this corresponding VC dimension, then we can find either a clique or independent set of sides, roughly n to the 1 over n log s. So instead of having 1 over s, we actually have just 1 over log s, but in exchange we need this extra factor n. So this takes care of strongly algebraic graphs. And in the case of just algebraic graphs, it's not much more complicated. So as I said, if I have an algebraic graph of complexity NDM, it is the Boolean combination of M graphs of strongly algebraic graphs. So now if I have a graph on vertices, which is the Boolean combination of M graphs, so each of them satisfies the conditions of the first lemma, so they avoid the mess and they satisfy the ultra-strong regularity lemma, then again they contain very large cliques or independent sets, so they contain cliques or independent sets of size until 1 over n log s, so I only gain an extra m factor here. And if I just plug in my just plug in the parameters or plug in my bound nets, then this essentially gives back this exponent we wanted, this NMD. So now I'm cheating here a bit, but this is essentially how we prove it. And so just let me finish with an interesting side note. So actually one can improve this ultra-strong regularity lemma for algebraic graphs. So we get the following pretty interesting, like asymmetric version of the ultra-strong regularity lemma. So we can show that if we have an algebraic, so algebraic graph of complexity and even, so sorry, instead here I wanted to write, so if we have a strongly algebraic graph of complexity and we have some parameter epsilon, then we can again partition into a polynomial number of parts in 1 over epsilon, such that now all but epsilon proportion of the parts have either density 0 or at least 1 minus epsilon. So previously here we had at most epsilon, but now we can actually clean these parts up, and we can guarantee that they are empty. But unfortunately, we still need to keep the dense parts. So for them, we can only say that they have density at least 1 minus epsilon. And so yeah, so basically that's it. That's all I wanted to say about our results. So thank you for your attention.
Thank you, István. Thank you. Let's thank István. Do we have questions?
Yeah, I have a couple of questions. I can try.
I have one.
So can you go back to this previous slide actually? So first of all, the 0 and 1 minus epsilon is interchangeable, right? You can do epsilon and 1, or is it different?
So here I wanted to write here strongly algebraic graphs. So now I want that edges correspond to non-zeros, so non-vanishing. And so it's not interchangeable.
Okay, it's not interchangeable. Okay, and so you could basically apply, like, you get bounded VC dimension property for this graph with some parameters, right? But what would happen if you, so here you improve this lemma separately, but you could apply the bounded VC lemma right away, right? How much worse would it be?
So actually,
just out of the fact that to shatter something, you have to have 2 to the projections, and then you know how many you have.
So in this lemma, the important thing about VC dimension is that when you have bounded VC dimension, that the number of sets of size s that you can realize grows as a polynomial of degree m. So and this is what we need. So if you instead of VC,
so this is what they use. Sorry, this is what they use in the proof. Just the property, just the polynomial growth.
Yes. So actually they state it this way, but if you look their proof, it's the only thing they use.
Okay, so you don't even need to do these manipulations. You can you have this property right away from this zero patterns, right?
Yeah. So it was a bit annoying because they don't state it this way. So in their paper, we had to cheat and say that, yeah, you can prove it in the same way. But yeah, it's essentially.
And another question, are there any other, I'll ask one and then there's one on the chat. Are there any other nice graphs or other graphs than this quasi half graph that you had that you can forbid? Do you know, is there anything else that maybe was not useful, but you also noted?
So are you asking about?
So here what you did, you combine this bounded VC dimension with this two-run thing, right? With this forbidden MS. Do you have anything other than MS that you can forbid? Or like
I have a similar
any
question.
other nice graph that cannot appear?
I have a similar question, to the Andrei's question. Is your proof heavily depends on MS or in some sense, or it's possible to forbidden some another graph?
Okay, so
this roughly the same proof.
So it heavily depends on MS. So for example, so in this paper, they don't even know if you have bounded VC dimension, then you can find polynomial cliques or not. So this is this Erdős-Hajnal for bounded VC dimension, and it's not known. So and bounded so bounded VC dimension means basically just forbidding a bipartite graph in a bipartite sense.
Mm-hmm.
And so that's also open. But in our case, this MS, so S was much bigger than N, and the way we gained is that here we have N, and so instead of just looking at MS, we had a bit stronger property.
Okay. István, there are two questions in the chat. The first is, do your results say something about the co-clique number of the polygraphs then?
Okay, so in relation to the polygraphs, so there the degree is p minus 1 over 2. So the degree of the polynomial that defines is almost the size of the whole graph. And for this doesn't say anything, unfortunately. So our result says something that you probably shouldn't take polynomials of degree, I don't know, some less than some polynomial of n or something like that. So it only says very big things, unfortunately.
Okay, and there is a second question. Please, recall, please, what is known about the VC dimension of calligraphs?
Yes, so was it calligraphs or polygraphs?
It's calligraphs in general.
Okay.
What can I say something about the dimension?
VC dimension. So I'm not sure if what can be said about this.
Seems like you have some kind of symmetric set family that you work with, transitive set family in a way, but I don't know any results, general results of that kind.
It's a specific family, maybe something useful is known. I don't know.
I would guess it's comparable the number of generators, but I don't know if anything better can be said.
Mm-hmm. Thank you.
Okay, do we have other questions? Okay, thank you, István. You was very kind.
Yeah.
Thank you. So let's thank István again.